Okay, Tracy, I think we're okay to go.
Yes.
All right, so hello, I'm Nikki Hickman. I want to welcome you to the opening session for AI4ESP workshop. This is the Artificial Intelligence for Earth System Predictability program. So we are here today to have a public plenary before we open our many sessions over the next month, and we will end this workshop in December. So quickly, I want to introduce Dr. Harriet Chung. She's going to welcome us to the workshop. She is the Deputy Director for Science Programs for the Office of Science at the Department of Energy.
Great. Thank you, Nikki. Good morning, everyone, and welcome to the Artificial Intelligence for Earth System Predictability workshop. We're so happy to see many of you joining virtually, allowing us to reach an even broader group of stakeholders. As many of you know, the mission of DOE's Office of Science to deliver scientific discoveries and major scientific tools to transform our understanding of nature and to advance the energy, economic, and national security of the nation. At the Office of Science, we spend a lot of time thinking about the future. We make projections about what research will help us solve future energy and climate challenges. We also anticipate what types of technology we will need and what their impact will be. But we also think about the future unknowns, the things that we can predict, but that we can prepare for by investing broadly in basic science. This overall strategy is especially important when we tackle the subject of climate change as the focus of this extremely timely and important workshop. If we consider climate change broadly, it is based on a lot of interconnected parts that combines everything from changing weather, precipitation patterns to ocean circulations, rivers and watersheds, melting sea ice and glaciers, greenhouse gas emissions, and to build infrastructure that bears the brunt of climate change. It is a complex system that we need to understand well enough to make accurate predictions. What the climate models and prediction need to tell us is how fast will climate be changing, even down to the local scales, and what will be the effectiveness of different technological interventions for mitigating climate change. The models need to be accurate to support this work. However, there is general consensus that the climate models have been under-predicting a lot of the climate changes that we see, and there's too much uncertainty in local to regional predictions. What this means is that we need to be more rapidly improving the accuracy of prediction, and we need to move fast. We need science to transition its results to climate solutions in a much more rapid way that we have been used to doing. And this is the main driver for this workshop, which is directly leveraging artificial intelligence, AI, to engineer substantial paradigm-changing improvement in Earth system predictability. We firmly believe that advances in climate science will be based on the exchange of ideas, on sharing knowledge, and even on sharing enthusiasm and curiosity. Science thrives on discourse, on collaboration, and on recruiting new generations of thinkers. Workshops such as this is vital because it helps us make connections and help us find novel and creative solutions. If there's one message I would like to leave with you today, is to be bold in your deliberations and not be limited by status quo to ensure that the US stays as innovative leader in climate prediction research. I'm excited to see the results from the workshop. Thank you for being here and bringing your expertise to the table. Thank you very much. Back to you, Nikki.
Thank you, Harriet. I really appreciate you being here. Harriet joined us on a bit of short notice. We had first the Secretary Granholm booked to talk with us, and then Deputy Secretary Turk. And as everyone understands that the Biden-Harris administration is not only taking the climate and EJ seriously, that they are setting very aggressive goals. And there's so many moving parts and so many different aspects and areas that we understand that everybody is actually getting called away, doing a lot of extra work. And as you said earlier, other duties as assigned have grown a lot in our area. So thank you again for being here. And I would like to also thank everyone for joining us, particularly those who have already been working with AI4ESP. I know a lot of you have put forth a lot of time, and I would like to extend my thanks to you, but also my gratitude to your family and friends. I know everybody has had a lot of tolerance and patience with us. We've worked some odd hours and we've had some interesting deadlines, and we are moving this forward fast, but there is a reason for that. So I would like to get into that just slightly here. So Scott, if you'll open the slides. So first off, what are we doing here? We're looking forward, as Harry was saying, we're going to be bold and we're going to look far into the future. And how do we get there? We want to define the paradigm shift that's required to employ AI or artificial intelligence, machine learning across our field, lab, modeling, and analysis activities. We're looking for non-incremental advancements here. We're looking to bridge the gap between the state of the art AI research and ESSD program needs. We're looking to harness that Earth Systems data that we have, the interagency relations and efforts, and it's a huge, vast array of data and processing and hardware capabilities, and the intelligence, the brain power across all of these is really the core of what we're doing here, is to bring that together. We're looking to harness DOE's computing resources, particularly exascale and the future computing resources. We're looking to consider domain-specific machine learning techniques, not just ones that were made for some reason and applied to something else. Maybe those are appropriate, maybe they're not. So we're looking to bring together the community of interest around AI4ESP to inform this ESSD strategic plan, for 2024-2028. So we're looking to support with our version of what is co-design when it comes to this specific area. How can that support the science priorities that need to be accomplished? What's the conceptual use cases that we can put forth? Sorry, got a warning there. In 1 to 3 years to get us on that road. And as Harriet said, bold ambitions. What is the possibility for the end of the decade? What's revolutionary and new in science and technology approach for everything from observing, data assimilating, modeling, simulations, analysis, and the prediction itself? Scott? So what led us here? We were listening that scientists and stakeholders are asking tougher questions. They're demanding climate projections. We're getting these climate projections, extreme events, storm surges, things that relate to human impact. The uncertainties that are in here are large, and we all understand that. And it's not easy to answer this, but we need to find a way to produce actionable information for our stakeholders that is good and solid. There have been success stories with respect to watershed science, cloud physics, modeling. We've had some machine learning applications in ARM, in SFAs, and other university grants. Oscar has committed to a significant investment in applied mathematics and machine learning and AI approaches with their dedicated centers. And there's not only a limited connection, but right now, there's a limited connection to our climate community. We're bringing that together. Barb and Gary have brought these groups together, from the program managers to the laboratory community, and we're extending that out beyond at this point. We know that there are science visionaries in the community, and those are who we believe we have reached out to, and we want a chance for them to bring in the scientific community view on where we should go and what that paradigm shift should be. Next slide. So the timeline kind of highlights of how we got here. We started in September 2020. We launched this project with a small multi-lab team. Myself, I'm at Argonne. Forrest Hoffman is at Oak Ridge. Haruka Wainwright is at Lawrence Berkeley, and Scott Collins is also at Oak Ridge. In October 2020, we expanded, we added in points of contact for some BOE labs to reach out further. So Ian Foster's at Argonne, Kirsten Cleese Van Dam at Brookhaven, Eric Hagberg at Los Alamos, Bill Collins at Lawrence Berkeley, Timo Brimmer at Lawrence Livermore, Dave Womble at Oak Ridge, Jim Eng at PNNL, and Andy Salinger at Sandia. So these also, we began meeting weekly with DOE, bi-weekly with our points of contact, and we moved to expand our community. First, by asking the community, what is this? What do you see? We put out a white paper call, and you'll hear more about this and how it designed out our workshop being 17 sessions that are like mini workshops altogether. But we were happily surprised when we got 156 white papers. And I believe there was well over 600 unique authors of those white papers that came together. And we saw the community ready to come together. They already had their ideas. They were already reaching across those boundaries. And so we really believe this is the prime time to expand on that and build. Oscar came in about this point, and 2 program managers joined us. We'll talk about that more in a moment. And then we also got some information from higher up in the administration to consider environmental justice more than we were. And so we've expanded that to be a part of what we're doing. As this grew, we realized that the workshop was not going to be very simple to plan. So we had a 2-day meeting in September 21, and we brought together all the session leaders. This was about 110 people to help us plan this workshop. And they have been invaluable to the insight of what we're doing and where we're going with this. Slide. So on the right, you can see in the middle, this is where our core team began. And the program managers from EESSD and Oscar that have helped us get there. This has been such a great collaborative effort between them and the POCs. We've had, they were meetings that go by incredibly fast every week because we just get talking about what we're doing and it blazes. With that, we added in these 17 chairs, and there are groups of people behind them that are working out in the community. I believe one of our sessions this week has 123 participants that will be actively trying to get at what we need for our workshop. So I want to thank them and their groups for everything they've done. We have many more invitations out to people that have not confirmed yet, but as you guys are hearing, this is a long workshop. We currently have over 570 confirmed participants, and they're representing over 160 institutions. And that to me is a really good sign of collaboration. We believe we can reach across interagency, we can reach into industry. And in this area, we think bringing these groups together can truly advance what we're working on. Next slide. So this is a slide that I kind of pulled from mine and Gary's and brought together because we want to move beyond the DOE MODEX example. So that's what the example you see in the upper right is. And this is showing from model to experiment, there are all these interconnected pieces and parts. There's data centers, there's field observations, there's analysis and data assimilation of the data that comes from the observations, parameterization is another data that's produced, scientific products. You also have process modeling that goes into how these work. And all of these things, you don't see arrows that are one way. And that is real. They are all interconnected. The heterogeneity of scale across what these groups are trying to bring together in an Earth system model. If you can imagine the microbiomes underneath the surface all the way up through the atmosphere, the scales are drastically different. And so we have to think about how we're predicting different, hybridized, moving forward in how do all these little pieces and parts affect one another. But you can't stick all of that into one traditional model. We know that, everybody accepts that. We're going to be looking to what hybrid prediction options we have. How do we lower uncertainty in our models, not just one little piece, but the overall? How do we produce results that the community and public can understand? That is hugely important to what we're doing here. With that, if you look at the area on the left, we're reaching out there. We have to co-design hardware, software. Look at our urban systems and our infrastructure and how things are being affected. Who are our stakeholders? Be bold, use 5G, use new sensor technologies. How do we make sure that we can advance the physics and the use of physics and AI within physics models? We want to go way beyond where we are. And this is what we're asking everybody here to define. What is the possibilities of where we should go and the direction and get us on our way of how we can get there. Next slide. Okay, so how we're going forward, it will be fast and efficient. So we have 17 sessions over 5 weeks with a 6-week for writing. In January, we intend to have our draft report, and how we intend to do that is we've asked each of these sessions to capture their content in the report weekly and provide a public readout the following sessions, so that everybody that maybe was listening in or wasn't involved in the discussion or unable to attend can hear in a really short summary what was produced in that discussion. We will have questions. There will be ways to follow up, ways to provide input, but we're planning to write this report as we go. So please do not hesitate if there's something you think needs to be said. We plan on having briefings for DOE in January and February, and having a final report posted so DOE can use it in their planning process. Our workshop link is on the bottom. Other registrations, the registration is there, the agenda is there, and there are pictures and bios for people who are on the agenda. Next slide. This is, in fact, one look of our agenda, and I apologize. It looks like my slide did not transfer very well, but luckily that's the last week. If you go to the workshop link, you will see this agenda. Today, we're going to hear from Gary Gernhardt, who's the director of Earth Environmental System Sciences Division, and Barb Helen, who's the deputy director for Advanced Scientific Computing Research. So these two areas of DOE are our prime areas that can come together and actually accomplish what we're trying to do here. So this afternoon, we will have a panel following that is led by Rick Stevens. And in between those, we will have the workshop charge, and we're going to present the state of the science as well. And so this is a quick view of what the participants up to this point, a very quick view on what the state of the science is, so that we can launch the workshop from there. And then we can use the workshop to figure out where we should go in the from the scientific community standpoint. If you want to communicate with us, please use our Slack workspace. The link is on the bottom. There's a QR code, and then we will be using the WS questions channel for any questions throughout the workshop. So please provide questions there. We will try to monitor that the best we can. If we can't ask them in the sessions, we'll provide information back in that channel to answer them. I believe that's my last slide. Okay, so this will occur. You'll see this more often, and these presentations will be posted as well. So you'll have a chance to look through them if you weren't able to attend. All right, the next slide. All right, Gary, would you like to give us EESSD's perspective?
Sure. So thanks, Nikki, and thanks, Harriet, before. I've got to say, we're finally here. This is an effort that actually took place starting almost a year ago. And I have to say, I am extremely excited about this from, at least from my division's vantage. The reason is that I like the idea of paradigm shifts. It's a cool concept that we don't hear about in terms of motivating the community into a new direction. I thank Nikki and the team for at least putting the energy and effort into doing this over the past year. And I would say that I'm really looking forward to the output of this workshop, especially the interim reports along the way, but the final product, which will take place early in the calendar year. Let's go to the next slide, please. Okay, so I've shown this slide to a lot of venues, most recently at our BER Advisory Committee meeting. It's a summary of our current vision and strategy within my division. As Nikki pointed out, and I'll just remind everybody that the report that we have, the strategic plan that we have right now extends through 2023. And basically that means through next year, we have to figure out exactly what are we going to do in the period through 2028. So workshops like this are a great way to at least chart the path forward for what goes into that strategic plan. And more importantly, how can we execute ideas early in that strategic plan so that we can have something really concrete that we can produce at least by mid or end of this decade. It's aggressive, it's ambitious. It's the kind of thing that we in DOE like to do because we don't like to take on easy challenges, but we want to have tough challenges that we can adopt and move them as fast as we can, because at the least, the idea of climate change, the use of AI, this is central to where the president's S&T memo focused on in August. but more importantly, it's the kind of thing that Office of Science really likes to take on because it's tough. And we are bold enough that I think we could use the laboratories, the universities, the private sector in meaningful ways to kind of collect our ideas together and make things happen. Let's go to the next slide, please. So what do we have at disposal, at least within BER and my division? We have research programs, but it's important with the fourth bullet in the top there, the Oscar programs, which Barb Helen's going to talk about after I finish, are those that we can leverage as much as we can to at least satisfy the vision that we're laying out within this AI4ESP workshop. We also have facilities which make DOE somewhat unique compared to other agencies. And these facilities are open to the community. I think most people know about them. The Atmospheric Radiation Measurement Facility, or the ARM user facility. Nikki is the Associate Director of ARM in charge of operations. And in addition to this job that she has with this AI4ESP, we have the EMSL out at PNNL, but we have a lot of these facilities which are more topical and program relevant, which is the third bullet. But again, the Oscar leadership, the big computers at Argonne, Oak Ridge, Berkeley, and others coming online across other labs are the kinds of capabilities we not only need to bring into AI4ESP, but I would say we're required to bring them in because we have to think about the future, imagine the technological developments along the way between now and the end of the decade, and be ready for them when they become available and not just wait. So our agenda here is to adopt these technologies early once they become available and not wait. And I think that's another thing which makes DOE somewhat unique, that we can move faster with that kind of strategic approach. The last bullet, money and political will on climate issues and the use of AI. As I hinted, the president's memo that was posted in August identified climate and AI as top priorities for the administration. They're also getting a lot of attention within Congress. And I think there's enough momentum there that this AI4ESP is perfectly timed to try and create this kind of paradigm shift to at least go forward. So this is where we need help from everybody in this workshop. Take bold action and think broadly. Think, I wouldn't say high risk, high payoff, but think in terms of what's possible and push the envelope to make it happen. Next slide, please. Okay, so this is just a quick summary of some of our programs within the division that have AI within their portfolios. It's not a complete list, it's just a snapshot. And I think I'm just going to go on to the next slide. Okay, and how will we respond to this AI4ESP workshop? Harriet gave some early comments on that. Nikki did too, but the main point is that we use these workshops to identify where we ought to be heading into, let's say, the next generation. And the product from the workshop is extremely important. In other words, without having a consensus from the community identified and documented in those workshop reports, it makes it more difficult to move forward. And that's why I put so much weight on making sure that that workshop report is complete, it's early, and we don't wait for too long for it. But I think Nikki and the team has really identified ways to at least make that happen and have something in our hand, at least by January, February timeframe. The second bullet I've already talked about, and the last bullet there is that we do intend to organize follow-up seminars and workshops because there are stakeholders out there, especially with the administration's new focus on urban, climate resilience, getting disadvantaged communities, minority serving institutions more ingrained in the kind of approach we take. That's going to be important for the seminars and workshops that we hold post AI4ESP. In other words, we're going to be moving this forward as we enter into late winter, spring, and summer of next year. And this is going to be a very powerful part of how we do that. Next slide. I think that was it for me. So I'm going to pass the baton back to you, Nikki, and you can introduce Barb.
Right. Barb Hallen is Associate Director for Advanced Scientific Computing Research. And Barb, we are really grateful that you all joined us early in the process and the support of this. I think if you can give us your perspective, we will all appreciate it. I think you're still on mute.
Barb, you're muted.
Oh, can you hear me now?
Yep. Yes, I can hear you now and
Okay.
see you.
Yeah. I want to thank you both, Nikki and Harriet, for the introductory remarks, and certainly want to thank Gary for being a great partner in this. So if we can go to the next slide. I think you've heard a lot about paradigm shifts, and early on, say in 2018, Oscar began to think about what AI was going to mean specifically for our math program. A lot of the work that had gone on in the early AI tools that maybe people were using up to that point had come out of the applied math program investments in optimization and linear algebra. So in January, we conducted a community workshop, much smaller than the one we're having today, and we tried to identify what are our priority research directions that we needed to go to do to make sure that AI was actually usable in scientific endeavors. So what did we need to do to move it out of, say, placing, a magazine in a grocery store so that I might buy it, so that we could, scientists could use it and understand its results. And as a result of that workshop, we identified 6 foundational and capabilities that we felt that Oscar needed to fund research in. Certainly one that's consistent with what we're hearing today, domain awareness for leveraging scientific domain knowledge in AI. That hasn't always been there. I mean, understand what the physical limitations are to, say, the modeling and simulations that we're developing. More importantly, we have to be able to interpret the results. So they have to be interpretable, explainable, and understandable. And we want them to be robust and well poised. So this is where a lot of the uncertainty quantification comes in. But we also want to do, another thing that's consistent with what we're talking about here. We want to make sure that we have the data. So we want data intensive machine learning so we can do automated scientific inference and data analysis, modeling and simulation, so we can predict scientific computing and intelligent automation and decisions report especially for managing and controlling complex systems. And I would say that the climate community, more so than a lot of other communities, were an early adopter of using ensembles to do their understand their complex systems on our large computers. So if we can go to the next slide. What followed up with the AI for scientific machine learning, I asked the ALDs from my 3 facilities, Berkeley, Argonne, and Oak Ridge, and certainly I think Rick is on the call, so he's familiar with this, Rick Stevens, to organize AI for Science town halls. We understood what the math needed to do, what math we needed to do, but what could AI do to actually change the scientific endeavor? What were the bold ideas? What were the big challenges? Could we change the way science was done in the next 10 years? So again, we had 4 town halls. They covered all 17 national labs. We had 39 companies, large and small, over 90 universities, and the 6 SC program offices plus the ERE and NNSA. And these took place in the 2019 timeframe. So we engaged the community, just like you, several of you probably participated in this, to identify the opportunities that could be realized by advancing and accelerating the development of AI capabilities, and the opportunities for the DOE Office of Science, as well as selected topics from energy and technologies, and how you could combine experiments, traditional modeling and simulation, and machine and deep learning. So if we can go to the next slide. This is an example that came out of the AI for Science Town Hall report. And this is the one, just one of the examples focused on earth and environmental sciences. And this is what, an idea that was maybe 2 years ago. So it'll be interesting to see how this idea advanced from where we are today. But certainly, applications of AI for earth, environmental, and climate research are in their infancy. The new challenges, new scientific discovery, and advances in energy security, national security, and adaptation, and resilience to extremes in our changing environment. So we want to revolutionize the development of process scale models by accelerating the process of discovery and model creation, rapid prototyping of the purpose-built models of Earth system processes and energy infrastructure, and emerging large databases such as those that you collect in ARM and other observational data that we might collect from satellites, so that we can develop a new generation of predictive models. So if I can go to the next slide, it's just a step back. This is what our applied math program has been investing in, where I think Nikki mentioned, microbes all the way, up to the clouds, and resolving these is multi-scale physics, multi-scale mathematics. So for a number of years, we've had these centers called mathematical multifaceted integrated capability centers, or MIMICs as we call them, where we really want to understand all the different types, and in our case, the different mathematical algorithms and structures that we need to pull together to really explain a complex system and a multi-scale system. And I'm just giving you an example from the physics informed learning for machines, or PhilM MIMICs center that we have. And one of the things they've been focused on is climate modeling, where they are looking at the ultimate multi-scale and multi-physics problems, where they're looking at time scales from seconds to centuries, and problematic interfaces, and of course, atmosphere to ocean, ocean to land, or ice and ice models, ice sheets, and that type of thing. And we're just going to review those in the next couple weeks, and then probably we'll do I think it's their time is up, so we need to actually release an FOA, or a funding opportunity analysis, for the next generation of MIMIC centers. If I can go to the next slide. Gary mentioned the facilities, and I just want to point out that we're currently in the process of deploying the exascale computing facility machine at Oak Ridge. Next year at this time, we'll be doing something similar like that in Argonne. These machines have been designed not only for the modeling and simulation that they're known for, but they're also been designed to handle large AI studies and and data analysis. So there, the balance of these machines are more focused on AI, machine learning, data analysis than we have had in the past. And so they will be good for high resolution modeling at Vanguard of large scale computing, climate adaptation, and earth science. And these are just examples of what these machines are being used for today. And certainly ESNet and NERSC have played a long, significant role in enabling data accessibility and transport in large scale climate and earth systems. And again, like I said, we're on the beginning of the exascale era, and I look to this community to really take advantage of what Oscar's putting on the floor in this year and next year. So if I can go then I think the next one is my last slide. Oscar, we mentioned that we have had a long history of working with the climate community, and it goes back to the climate change prediction program. It was my first familiarity that I got with the climate community, where we were linking emerging technologies in high performance computing to the development of computationally efficient and numerically accurate climate prediction models. That's essentially what we're doing today. We're going to connect high performance computing, AI, machine learning with climate prediction. And what will that help us do? What can we do tomorrow that we couldn't do today? We've had a long history. Again, the last 20 years, we've been partnering with BER and the climate community through our SciDAC Scientific Discovery through Advanced Computing, or SciDAC program. The image on the right is just an example of one of our the partnerships between Oscar and, in this case, researchers from Los Alamos and Sandia to simulate the flow of ice across Antarctica. Again, some of the tools that we developed have made us look at very, zero in on the parts of the simulation that we really want to look to. And of course, the last thing I want to bring up is the exascale computing project. We were one of the projects applications that we're supporting in the exascale project is the Earth Systems modeling project. And we look forward to it actually running in the next couple of years on exascale, running their challenge problems to make, because we wanted to make sure that they could take advantage of the exascale machines day one once the machines were put on the floor. So like I said, I'm happy that I'm working with Gary. I think there's a lot that Oscar can bring to the partnership. Now, I just briefly talked about the computer science or the applied math part of this, but certainly computer scientists can help with portability and some of the other tools that we're developing. So I welcome this partnership, and I think that's my last slide. And with that,
thank you, Barb. I did sneak a little slide in there at the end of your presentation. No, I absolutely, the community of people that are invited to this absolutely buy into what all Oscar associated scientists can bring here. It's very clear from the invitations and the confirmations that have been sent out. And I'm working on some demographics for you, so hopefully I will have those very soon. So we have a little bit of time here, and I wanted to do just a quick question and answer. We put out a few questions, or we put out for a few questions very recently, just to people that the session chair leads, as well as points of contact, the core group. We wanted to have a few things to ask for you, but if you have other questions for Gary or Barb or myself, please put them in the WS questions channel in the Slack workspace, and we'll try to get those answered as well. So my first question is, this is probably the largest workshop of its kind that marries climate science with applied math, computer science, and artificial intelligence. Is DOE planning to make serious investments to further the ideas that can come from this workshop? I'm not sure how we can raise hands and duke it out. Thanks, Gary.
Yeah, maybe I'll start with this and we can have either Barb chime in or Harriet, but yeah. I have to say that's a question we should have anticipated, so I'm not totally surprised. I think the simple answer is that the FY22 budget request, which everybody's seen, it is favorable to climate. And the administration and Congress are both elevating the importance of science and technology. They're focusing on a zero carbon economy by 2050. So anything involving S&T to help us get there is important. So I can't really speak beyond that because we don't have an appropriations yet. We can't talk about 23, but the main point is climate and AI are both priorities to the administration. And I would just say, let's see how the appropriations play out. But I think more importantly, let's just not hold back with ideas from the workshop, and let's just look forward to the workshop report, because that's going to be important. I don't know, Barb, if you wanted to chime in, or Harriet,
yeah.
But.
Well, if I can add one thing, Gary, I think, as you well know, I mentioned SciDAC. Mm-hmm. And one of the things that's happening this year is we're re-competing our partnerships. And one of the partnerships we're re-competing is the one with Oscar and BER. So there might be some opportunities there. I haven't seen the funding opportunity announcement yet, so that could be an option. The other thing is, I think, we're always interested in input, and certainly Oscar's going to be developing a long-range vision for Oscar. So a lot of this will play into what we're doing as well. So back to you, Gary and Nikki.
Wonderful. Thank you very much. I do think there will be a lot of people in this community that have come together prior to this meeting, and the collaborations that come out of this meeting that will be very excited about that specific SIDAC interest you mentioned there. So for our next question, what do you feel are the most important things that climate models should be predicting, maybe as a way to help guide this workshop?
Okay. This is Gary, obviously. So in a way, I'd like the workshop attendees to help answer that question, but I'll give you my selfish answers. And that is that we need to focus on the predictability of tough issues. These are issues like how do we predict extreme phenomena? In other words, are there going to be significant changes in extreme events as we march forward, especially in areas now that are heavily populated with diverse communities? I think that's going to be something we have to focus a lot of our attention on over the next years. And that involves things like extreme phenomena that affect urban regions. It could be just coastlines. It could be mountains, anything that's difficult to predict right now. So I'm thinking of flood, drought, wildfire. I mean, wildfires are hard to predict, but once they're triggered, we should be able to start making more powerful statements about them. The workshop is focused largely on water cycle, but water cycle touches so many things that it was a way to at least constrain the conversation. But going forward, beyond this workshop, we're gonna have to think broader. And I would say since this whole workshop idea was conceived, the topics of environmental justice started to be incorporated. So I would say whatever we can do to take on those issues, because those are really complex issues, the better off we're going to be. So I'll just say thanks for that. Barb, I'm not sure. Anybody
Yeah,
else?
I just want to add one thing that's come out of our exascale projects and to think about impact. You mentioned, of course, sea rise on urban areas and wildfires. But another thing to think about, and it's been in the news a lot lately, is what is the impact of extreme events on our power grid? Are we prepared to handle it? What do we need to do? What kind of sensors do we need to have in place? I mean, it was a number of years ago that the derecho went through out here and knocked a lot of power lines down in West Virginia that impacted our, the ability, for people to have power. And I'm sorry, without power right now, we can't compute. So, I mean, there's a long-term impact. So I think we have to really be able to think about, understand the impacts of extreme weather events, not only on our power grid today, but also the renewables as we're thinking about putting them on in the future. So back to you, Gary.
So I'm going to reinforce Barb's point, and that is that when we think about predictability, we're looking at the interdependence of all the components of the climate system that include infrastructure, because there are feedbacks that go both directions. But I think one of the tougher questions to deal with involve cascading failure. In other words, it's not just a response to a single extreme event, but if you have sequences of extreme events, one has to be able to predict the recovery between the two events as they might occur in sequence. That's not well done in our models. So I think giving some attention to that might be really important, especially as we try to link climate science towards climate solutions. All right, thanks.
Okay, and I think you may have answered a question that we had online while you were doing that. Very good. Okay, so next question. Since this was one that came in when we was talking about COP26 next month. What is your take on the message that's intended to be sent to the international community that DOE is taking a bold step in the climate prediction science, not just climate techniques?
So I'm going to take a stab at this because I've been part of the weekly COP26 meetings in DOE. And that is the DOE is sending a delegation over to COP26, and I think most people know that's taking place in Glasgow, Scotland, in a few weeks. It's going to be really for the first half of November. The secretary's going, our deputy secretary's going. It's going to be a pretty big event. And this question was more directed towards Dave Turk, assuming he was going to give the presentation today, but he was pulled out to an emergency meeting at the White House about an hour and a half ago. But he is going to be, both the secretary and deputy secretary are going to be giving presentations at COP26. It's on DOE's ambitions in climate science and technology. And I'm well aware that there has been attention given to what E3SM is doing and where it's heading. And just a point I'll make to the audience here is that, and that is the E3SM has been interacting with the UK, the EU, a lot of international organizations, so we can figure out how to leverage those capabilities as we go forward. I don't think I can answer much more to this because it's more tailored towards Dave Turk, but all I can say is that we do intend to have our capabilities coming out of AI4ESP, not just to serve climate science here in the US, but stakeholders globally. I think that's going to be important to DOE and to the US. I'll stop there.
Thank you, Gary. You answered why I thought it was important to actually touch on this for this community. And COP is the UN Climate Change Conference. For those of you who maybe don't know that, I bet everyone here probably does. But also, just with respect to the international community and also interagency, everything that we've worked on in AI4ESP, we have tried to make transparent, open. We are very much intending to work with all of the communities that are involved here through open source, fair data practices. We want things to be helping more than just the person or group or agency that's developing it. So we really, I think everybody is ready for that paradigm change in addition to where we're trying to go with respect to AI4ESP, but under the hood. Okay, next question. With respect to stakeholder and public skepticism of scientific results and relatively low-level understanding of how AI techniques work, how do you envision that we can promote trust and engagement by decision makers, stakeholders, and the general public?
That's an interesting question. I'll take a first start, and there's no doubt we need more public engagement with our research. The National Academy has held a number of communications workshops on how our community, how our scientific community can engage in a more effective way with the public. I think we need to follow a lot of that advice. Even within DOE, we're doing the same thing. We're talking about having DOE-led workshops on climate communications. And I would say just stay tuned on that. But I think the ideas coming out of the administration for FY22 are going to provide a great avenue for this. I think people have heard about the urban integrated field laboratory concept, the new climate lab and centers, the National Virtual Climate Lab. I'm not going to go into those in detail because they are in the President's budget request. But these are going to be the good venues for us to have stakeholder engagement and the kinds of things we do so that they can feel like they're part of the process and not just end users somewhere down the pipeline. And I think that's going to be the key to how we go forward. But it's a good question. Thank you for that.
Now, Barb, do you have a take on that, particularly with respect to AI being difficult to understand sometimes?
Yes. And this is where uncertainty quantification becomes very important, and making sure that we're building that into our models so that we can narrow the error bars on what we're predicting. I think we need to, I agree completely with Gary, but I think we also need to take a conservative approach and actually look back at some of the data that we've collected over the number of decades that we have climate data and see what kind of predictions we could have made, what types of data we were missing so that we could have made more accurate data, so that we can make sure that we have that data going forward and that we're sharing the most recent data and this is where the interagency community comes, it becomes important, because certainly NOAA and NASA and DoD have other observations that we don't have. So the ability to be able to share this data and put it, in a format that we can use it in our models, I think is going to be important going forward. And hopefully we can, weather prediction for hurricanes and other storms gets a lot of publicity. But if we can make those predictions better, I think that the public will begin to see the benefit. But we have to proceed with caution as we go forward, because we don't want to make any glaring errors, or at least not as many as maybe we might if we don't pay attention to uncertainty quantification.
Definitely. Observations and data sharing is very close to my heart.
Yeah.
For those of you who know me.
So
Okay.
Nikki, could I quickly
Yes,
jump
please.
in with some real remarks? I just want to echo what Barb and Gary have shared. Another point I want to mention is that this is really a almost historical moment that we have so much information to share. So I think in addition to the opportunity, I almost felt like this is a responsibility for this community to broadly and concisely share the challenges and the opportunities, and in a credible way. So in addition to kind of deliberations, there also an opportunity to come up with a communication strategy, almost put that kind of framework in place as you continue this weeks of workshop, and what kind of outputs that you could then build a communication strategy to communicate within your community, but also to the public. And that is probably equally important to this paradigm shifting breakthrough R&D opportunities. So just wanted to plant that seed early in the process. So as you're building the R&D portfolio, what kind of drumbeat message that you could then put in place going forward. Okay, that's it. Thank you.
Thank you. I think that is a very important message that we need to hear.
Mm-hmm.
All right. So AI is very useful, but requires a lot of computing resources to succeed. What's the plan to meet the burgeoning demand for those resources the widespread use of AI will require, particularly where computers needed may not be the same type suited for modeling needs?
So
Barb, you want to take
Gary,
a
you
stab
want
at
me?
that?
Because you were going to say that. Well, I've already mentioned the fact that 5 years ago we started, making plans to put exascale computers. Well, actually, we started longer than that, but to put exascale computers on the floor. So I think that will go a long way to meeting the high level demand. These all of the both of the exascale machines, the one at Argonne and the one at Oak Ridge, will have a large number of GPUs to help do AI calculations and large memory to actually foster this. But we're looking forward, and this meeting will help. And Oscar, we're looking forward to what the next generation machine should look like. And certainly, the facilities are all testing AI accelerators. The next generation might have AI accelerators on it. But we are looking, I don't have the answer today, but we certainly are trying to figure out what we can do to make sure that people have adequate resources as we go forward, because this is a big problem, because AI is going to be everywhere, not just scientific calculations, but the people at the national labs. It'll be, helping operate the labs. I'm sure universities are doing the same things, but we have to make sure that the compute is there to support this effort.
It's
Gary?
definitely a real challenge.
I can't add much more to that.
That is definitely a real challenge. A good one here. How important is it that DOE works with the other agencies on AI4ESP? Yeah, all three of you can.
Well, there are a lot of agencies invited to this workshop, and I'm going to say it's extremely important. DOE it has a somewhat of a unique niche that we focus, at least Office of Science and AI4ESP is focusing more on basic research. But a lot of the other agencies that have AI and machine learning investments, it's often more on the applied side where they start to exercise existing methodologies to at least address some of their challenges. So I think it's in DOE's interest to make sure that the basic research accomplishments that we can develop coming out of AI4ESP or similar activities can be advertised broadly across the federal government so that the other agencies can pick it up a lot faster. So even having joint projects in some way or tighter coordination, collaborations. NSF has a major investment in AI and computing. They also have it in climate predictions and Earth system modeling. But it's not just, I would say the obvious agencies that we should target initially would be NSF, DOE with NSF, NASA, NOAA, the Defense Department, the intelligence community. There are a lot of other agencies that have a huge interest in what we accomplish. And we need to open that dialogue and keep that dialogue in place. I don't know, Barb?
Yeah, I agree completely with you, Gary, because, based on my years of experience at a lab and now at DOE, if we aren't bringing those other agencies along, then there's always some reluctance of using our software and what we've done because they didn't write it, they didn't build it themselves. But I think we have the ability to really advance the field in this case, especially with the exascale project and with what we're proposing here. And I think the communication, sharing, making sure that everybody is involved in what we're doing helps alleviate some of the fears of using unknown code. And so I'll just end there.
Harriet, do you have any comments on our reaching beyond DOE?
Not specifically, but is that for me? I'm so sorry. I was multitasking. Agree with what Barb and Gary said, and that I think it's also part, in my view, part of this communication strategy. We need to make sure that DOE strategy is very well integrated and aligned with the whole of government strategy, and making sure that the coordination, the messaging are both well aligned.
Thank you. We will definitely try to do that. Somewhat following on that a bit, AI4ESP looks to be significantly targeted at the Office of Science at DOE. How can we as participants help the workshop impact the rest of DOE complex, and for that matter, the rest of the science enterprise in the US? So I think we just stated the importance. How can our participants help with this?
I'll take a first stab. And I'm going to say this because I came from the National Lab before joining Office of Science. And that is the labs have funding from not just Office of Science, but they have it from ERE, Office of Electricity, FE. You go across the board, NNSA. But the point is they are perfectly positioned to, let's say, demonstrate and transition the success stories from AI4ESP into applied problems. And I think that's something which we need to promote as much as we can. The other thing is we can come up with use cases, and I think we may need to have a DOE town hall at some point with all of DOE and not just Office of Science. Because if this is truly going to be a paradigm shift where we want to have immediate impacts across the department or the federal government, getting the word out so everybody's aware of what we're up to is going to be important, because then they can start plugging in along the way. Barb, do you have anything to add to that?
Yes, we're planning that town hall, actually that workshop right now. And I think the first date will be December 7th, 8th and 9th. I have it written down here, but we are planning a workshop, and we kind of stole your name. It's called AI at DOE. So,
Great. We're happy to be connected, however.
Yeah, and I think that, one of the organizers of that is Valerie Taylor right there at Argonne.
Great. We will coordinate around our writing meeting that isn't planned
Yeah.
yet and make sure that we can participate however we can be helpful. Okay, so I think I'll make this probably the last one, but I've got a bit of a challenging one here. We'll need more scientists who are well trained in both Earth, including climate science, and AI practitioners to do this well. What is DOE's strategy on workforce training recruitment in the area of AI for science, especially given the steep competition from industry?
Barb, you want to say or shall I?
Well, I've been investing in computational science, the Computational Science Graduate Fellowship for 30 years. And that's exactly what we are trying to do. Now, we've been fortunate that Congress has increased our budget, so we hope to be able to support more of those. Now, my problem is we haven't gotten a lot of climate scientists coming through CSGF lately. So if there are people, institutions out there and you have students, please, I think the application is open. But certainly that's one of the things that we're trying to do, and the other is build a community of computational science. And I think there's been a lot of focus on reaching out to underserved areas, and we're trying to do more and more of that so we can bring more people into the area. And we have to begin to recognize that people don't always take a straight linear path to get to maybe a master's or a PhD, and we've got to figure out how to support those people so that we can keep them on the path to support us in the future. So with that, I'll turn it back to you, Gary.
Yeah, I'm just going to add a thought to this, and that is that we often have town halls with the big conferences like the AGU or the American Meteorological Society. And I'll just say I'll take it on to at least make sure that the word gets out to the community that the directions that we intend to take, let's say post AI for ESP, once we have our workshop with the key findings from the workshop, once we have that in print, I think we need to have somewhat of an aggressive campaign where we have town halls with the community where they get the signal that we're taking this seriously. And they often respond if a message comes out through town halls that we're taking this seriously, this is the direction we're going to take, and that we're going to be expecting our future investments to combine, let's say, Earth system prediction, climate modeling, AI, and that we're going to need people who are trained in both areas to do it right. So that might be the incentive for the academic community to kind of prioritize this. And it will be a signal to people to start strategizing how to do it.
Gary, if I could interrupt, we do actually have a AI for ESP town hall planned for both the upcoming AMS and AGU meetings. So that will be a great way for people to engage with this community post-workshop.
Great, thank you.
Thank you, Scott. And Gary just reminded me of something I have not thought about on the workshop report, and that's in print. So I will work on that before December, and we'll have a plan. I am gonna, one more thing, well, two. Maverick, keep your question. I think the next presentation may answer it, and if not, we'll address that then. And then Paul had a question. How do we balance the AI focus with the science focus outcome? And how do we avoid doing AI for AI's sake? What happens if there's opportunities in front of us that AI is not the right tool?
So I'm going to take a little stab, and maybe Barb can take it too, but we don't often know if any particular AI methodology is going to work. Our goal is to improve, let's say, to reduce the uncertainties of predictions in clever, innovative ways. But I think there's enough good success stories that AI and machine learning have really made a difference in, let's say, parameterizations, or with models of, say, watersheds. We've got lots of success stories there. So we need to build on those. The other angle I can mention is that co-design is something which we embrace here within DOE. And that's somewhat unique to DOE. I haven't seen that used as much with other agencies, but AI for ESP is kind of building on the co-design idea. In other words, you don't just go down the pathway of improving a model, down a separate pathway on improving methodologies for AI, and then connect them at various points. But if it's co-designed from the start, it's a much more rapid and efficient way to do it. That's my opinion. But Barb, if you want to comment.
Yeah, let me just add on to that. You said my favorite word, which was co-design. I think that's another power of bringing the applied mathematicians and computer scientists to work with the climate scientists. We may have, say, because of the computer science, a better way to write some code or more efficient code or, a new algorithm that might be better than AI. So I think it's bringing all that knowledge together to work on the problem, identify what are the right technologies for the right part of the code. And I think that's really the gist of this network, is to figure out, or this workshop is how we can work and do a co-design model to put our best foot forward using AI, using new math algorithms, multi-scale math, physics, uncertainty quantification. I think that's what we're looking, for the attendees to tell us what to do.
And from a workshop perspective, exactly what Barb said is what we're trying to do here. We have no intention of peanut butter spreading AI on things. That's not going to work. Nobody is under any assumption of the such. We are believing that there will be techniques that don't exist yet that we need. There's going to be, that co-design goes both ways. And so we expect that the findings of this workshop will be very challenging and will require joint and collaborative work in the future. So please think about those things, and definitely we want to hear those. So don't hide them. I think let's move to our next presentation. Barb, Gary, thank you very much for answering our questions, in addition to telling us your perspectives on where we should go in the future. And now we will tell you where we think we ought to go with these other parts. So I hope that is our intent. So thank you very much. And I know Harriet had to leave, but we are very grateful that she popped on as well. Okay, so our core group here, Sel, Forrest, Haruko, and Scott. I'm not going to present in this because these other three are awesome, and I cannot tell you how grateful I am for this team. From reading white papers to analyzing white papers to understanding even from the focal areas of the first papers to the sessions in the end. This has been an amazing collaboration, and I want to thank our laboratories for allowing us to do this very lab agnostic. It has been a wonderful collaboration, and I think you can see from the workshop set up that it has been a successful one. So I will turn it over to you guys.
Okay, this is Haruko Wainwright from Berkeley Lab. I will introduce the structure and charge in this workshop. Next slide, please. So we started our workshop planning from these white papers submitted by national lab, university, and industry researchers. These white papers are publicly available on our AI4ESP website. I would say that this is a significant collection of really exciting ideas and also insights on how we can use AI machine learning in a variety of topics in the Earth System Predictability science. Next slide, please. So it took us quite a long time, but we have synthesized these 156 white papers, extracting insights and highlights for workshop planning. So we looked at different aspects of each white paper. We looked at the responsiveness to the three focal areas in the white paper call, AI for data acquisition, AI for modeling, and AI for knowledge discovery. We also evaluated and considered the relevance to the EESSD program domains, including EESM, Earth Environmental System Modeling, ASR, Atmospheric Systems Research, EES, Earth and Environmental Systems Research, and Data Information Management. And we have seen that many of the white papers included topics relevant to 2 or more programs within this EESSD programs. And we also evaluated what are the different AI techniques and opportunities and needs articulated in the white papers as well. So after many discussions, we have developed the matrix structure of organization. One dimension is the Earth System Predictability topics, and the other dimension is the cross-cutting AI machine learning topic. Next slide, please. So here is the list of the Earth System Predictability topics. We have 9 topics here. I will explain them later. The purpose of having these topics is to have a focused discussion on each ESP topic so that we can have in-depth discussion, deeper evaluation, deeper discussions on the AI machine learning needs and opportunities. At the same time, we want to identify quick wins and also the connectivity across the subtopics as well. We, of course, didn't want to create silos, but we thought that some grouping is necessary to make organization and discussion much more tractable, and also make discussion much deeper into the details of AI machine learning methods. Next slide, please. So this is the distribution of 156 white papers across each ESP topics. First, we can see that atmospheric related topics account a third of the white papers, including atmospheric modeling, aerosol clouds, and large-scale climate variability and extremes. And another third is hydrology-related topics, which are divided into watershed science, hydrology, and ecohydrology. In addition, we identify critical topics in the program, including human urban systems. Gary and others mentioned many times in this meeting so far, and also land modeling, including fire and ecosystem dynamics, as well as coastal, ocean, and ice dynamics as well. Next slide, please. So from here, I will introduce each of the ESP topic. First, the atmospheric modeling group focuses on atmospheric dynamics across the Earth, including convection and turbulence and radiation, which are the critical parts of E3SM, Earth system models. The aerosol and cloud session focuses on more detailed physical processes such as cloud formation and aerosol cloud interactions. Next slide, please. So land modeling group includes mainly plant dynamics, simulating wildfire and also agriculture application based on satellite and various data sets. The ecohydrology group focuses on more detailed processes in plant water cycle, including plant hydraulics, plant growth, evapotranspiration, as well as their interactions with soil hydraulics. Next slide, please. So in the hydrology related topics, watershed science focuses on hydrobiolochemistry, more detailed processes relevant to water quality, nutrient cycle, based on laboratory to field scale investigations. The general hydrology topic, hydrology session, includes a little bit larger scale hydrological processes compared to watershed science from regional to continental scale, including water resource problems, groundwater hydrology, and water-related hazards such as flooding. Next slide, please. The climate variability and extreme group focuses on ENSO, atmospheric river, and other large-scale variability and extreme. And the coastal dynamics ocean ice breakout session will focus on dynamic processes at ocean land ice interface, including sea level rise, storm surge, and coastal ecosystem carbon cycling aspects. The next slide, please. Lastly, the human system and dynamics group includes topics related to anthropogenic activities, including energy, water, land nexus, urban environments, and also land use cover changes. Next slide, please. So this is the list for the cross-cutting AI machine learning topical sessions. The first one, the data acquisition, includes edge computing and other different sensor technologies and how to include those data sets into climate and Earth system models. Surrogate models and emulators are, I would say, the most popular topic among the white papers. Neural networks and deep learning are, of course, another popular topic as well across the white papers. And hybrid modeling and knowledge-informed machine learning are sort of emerging fields and very hot topics right now, coupling machine learning AI with physics simulations, as well as science and expert knowledge. Explainable, interpretable, trustworthy AI is another hot topic right now, which represents the departure from black box AI machine learning approach for more sort of improved interpretability. And knowledge discoveries and statistical learning group at breakout session will include a class of machine learning methods to extract critical science knowledge from large data sets. The last one, AI architecture co-design, focuses on the hardware development, HPC development relevant to the simulations related to Earth system predictability. So in these cross-cutting breakout sessions, we aim to identify what are the applications across Earth science topics areas, what are the biggest opportunities and needs in development in the next 10 years. And also we want to identify what are the quick wins and what are the best areas to identify the selected AI machine learning method. Next slide, please. So here is the charge for the breakout sessions throughout this workshop. Each breakout session aims to answer these questions. The first one is, what are the grand challenges in each of the Earth system predictability topic and cross-cutting topic that can be uniquely and transformatively addressed within DOE? What are the experimental data and modeling opportunities and needs to advance the development and applications of AI machine learning approaches to address these grand challenges? The third question is, what research must be conducted as the next step to address these grand challenges? And what can be the research and AI machine learning priorities? And the last question is, what are the near-term, 5-year, 10-year goals for developing and applying machine learning and AI approaches for these grand challenges? And of course, we encourage the coordination and collaboration across these topics area as well. The next slide, please. Nikki has shown the workshop scheduled earlier. So the workshop is the mixture of the public sessions shown here in green for plenary talks and report out session, and the invitation only sessions shown in the red for in-depth discussions. And after this plenary session, today we have atmospheric breakout session, tomorrow we have two plenary talks, very exciting talks. One by Professor Amy McGovern and the other one, Professor Pierre Gentin. We know that this is a big, really mammoth workshop, and we appreciate everyone's contribution. And next slide, please. And we are happy to take any questions in Slack for the current slides and the subsequent sessions. Thank you. And we can move to, I guess, state of science presentation. And I will pass to Scott.
Thank you very much, Haruko, for that presentation. I'm just going to share my slides. Can I confirm, Haruko, that you're able to hear me?
Yes.
Excellent. Thank you, Haruko, for giving an outline of the workshop structure and the charge. Before we head off to our panel discussion and to really getting the workshop underway with the modeling session this afternoon, we wanted to give an outline of the state of AI science as it is being applied to Earth system predictability. Again, we're led by very, very capable Nikki Hickman, who we really have come to believe is actually 5 people rather than 1. And I've thoroughly enjoyed collaborating with Forrest, Haruko, and the rest of the team at DOE and our points of contact at the lab. The material you're about to see was given to us by the session chairs in collaboration with their fellow attendees. So I want to thank them in advance for the materials they have provided in laying these foundations. As Haruko showed, we are going to break this down into the Earth system predictability topics and the crosscuts, and I'll be assisted by my colleagues Forrest and Haruko in presenting this. So let's start with atmospheric modeling. Currently, machine learning and artificial intelligence is heavily used, or has been used, in physics parameterization development. The idea being, if you can train a network or other emulator, it can perform calculations a lot quicker and be a lot lighter than maybe an existing parameterization scheme that may be more complicated. Also, we can leverage things like deep learning. You can see in this list here, we actually have a couple of topics which will be in similar with other both crosscuts and Earth system predictability topics. This is okay. As Nikki said at the beginning, cross-fertilization and discussion is very much encouraged. If we see during the workshop that we get similar output from each individual session, well, that shows that there is agreement and correlation across this workshop. Another area machine learning and artificial intelligence can be used for is an interpretation of atmospheric and climate simulations. Currently, some successes have been identified. New approaches are being used and being explored, and we really hope to elucidate these during this workshop, especially gaps in the existing ecosystem of algorithms that exist. In the area of aerosols and clouds, where we're actually looking much more at maybe data collection as well, AI has been used for smooth curation and quality insurance. Things like anomaly detection algorithms are very useful in looking at data sets as they come in to look at outliers in collected data. However, we still need faster, better representations and dimensional reduction using AI and objective quantification correction of model structure deficiency in aerosols, clouds in the Earth system. Climate variability and extremes, so looking at both observational and existing model data to look at this. This is where AI can be particularly useful because many algorithms that have been developed are all about feature identification. Think about Google Street View trying to remove number plates and faces by keying into certain structures through convolutional neural nets and other. You can use this information, or you use these techniques to identify things like atmospheric rivers, tropical cyclones, and fronts, the same way that an expert might look at model output, let's say from the GFS or high resolution rapid refresh, and go, I know that is a baroclinic zone, and I know how that behaves. Things like bias correction, and reduced order modeling as well, and also really kind of automating that analysis pipeline as well. And now I believe I'm going to throw it to Forrest, who is going to take us through land modeling.
Thanks very much, Scott. So some of these points for land modeling kind of reiterate some of the items that Scott mentioned on the previous slides, in particular with atmospheric modeling, but we'll also have some examples here in some of the other topics. So a key aspect where machine learning can really come into play is through model data integration to help us improve the predictive skills of models. So that includes developing advanced surrogate modeling approaches to predict responses over parameter space, using those models for model calibration with gridded observations, satellite measurement, and with point observations as well. AI for model bias correction, and then data worth analysis to inform timing and placement of new measurements. So sort of a network analysis approach or graph analysis approach for deciding where to make additional measurements and which of those measurements is really required. Representing physical processes or chemical or biological processes. So AI can replace submodels or individual parameterizations with physically constrained surrogates for efficiency and for uncertainty quantification, for instance, in wildfire prediction. AI models may be used within model hierarchies to develop levels of complexity, particularly for scaling and uncertainty quantification. And these, these issues are important across all of the earth science system and across all of the components in an Earth system model. AI can also inform missing dependencies, causalities, and functional relationships within data to help improve the physical understanding and processes represented in land models or any component models. To help us also to understand the processes behind the effects that we observe, we can use artificial intelligence to look at the key relationships among environmental variables. So some of the key challenges that are identified by this group are computational expense of land surface models. So that limits the number of ensembles we can use for training. Scaling knowledge from intensely observed sites for global relevance. So how do we make that extrapolation? How do we do that inference for point scale data to a larger domain? Sparse measurements for key variables. Again, overfitting to a limited amount of data, and out of sample extrapolation. Next slide. So for ecohydrology, we came up with a few key examples that highlight approaches and some of the challenges that they solved. So Mishra et al. Recently compared 4 different machine learning approaches with a traditional regression kriging approach for predicting surface soil organic carbon stocks for the northern circumpolar permafrost region. And they found that an ensemble median of these machine learning techniques that were employed exhibited the greatest prediction accuracy. Also recently, Masood et al. Used a polynomial chaos expansion emulator and sparse grid sampling for models of increasing complexity, including a hydrological, eco-hydrological, and a vegetation dynamics model. The emulators perform better for lower complexity models, but by using dimensionality reduction, they demonstrated improved emulation of even the most complex model. Burke et al. In a third example employed random forests to identify the relative importance of biophysical and climate drivers in predicting effects of fuel treatment in forests. So here's a very direct application that's useful for management purposes. Interactions between biophysical setting, climate, and fuel treatments are very complex, and of course they have nonlinear effects on forests, water, and fire. So it's complex to figure out how to tweak any of these parameters in order to get a desired outcome. But the importance of drivers emerged from the analysis, and then the same random forest models can actually be used to test out other parameters to without having to run all of those individual models again specifically. Next slide. Yeah, human systems and dynamics. So anthropogenic activities are probably the largest single driver of uncertainty in the future Earth system. Because humans are embedded within and influence the dynamics of the Earth system, and that human dynamic is very hard to quantify. And so, but those kinds of problems, as we heard from Gary and Barb and Harriet this morning, are inherently interdisciplinary, as we were talking about impacts of storms on electrical systems, for instance, and utilities. The state of the art is incorporation of human systems and dynamics into Earth system predictability using any method. It's still early days in doing that, and trying to incorporate human systems even into the standard Earth system models we have now is a challenge. So how it's done varies across scale, both spatially and temporally. So at smaller scales, using machine learning to understand Earth system effects on human sectors is done. And there are some examples in here that you'll be able to click on once we post the slides, which will happen at the end of today's session. Larger scales include simulating effects of people on the larger Earth system, including through wildfire dynamics, climate change adaptation policy, and agriculture. And then incorporation of empirical understanding of human systems into the Earth system, of course, varies by technique and approach. Some black box machine learning implementations are sometimes used when we lack domain insights, and non-machine learning implementations of directional impacts between human and Earth systems at varying scales is done, including synchronous coupling between human and Earth system models and agent-based models that have been used to understand decision-making at regional and global scales. And next, I'll hand it off, I believe, to Haruko.
Yes, so I'll take over from here. So hydrology. The hydrology community has been, I would say, the early adopter of machine learning, thanks to the long tradition of applying statistical methods, and also many standardized data sets, such as precipitation and streamflow data sets, for example. I would say it is a pretty mature field of machine learning application. The main applications have been improving the predictive understanding of water resource, water availability, and water quality, event detections, identifications such as flooding, droughts, as well as the prediction and forecasting of these events, stream flow, and water availability. There have been various methods, machine learning methods, applied into in hydrological application, including deep learning and its variant, physics constrained machine learning, and also process model data coupling are, I would say, emerging topics right now. Next slide, please. So watershed science, on the other hand, focuses on more detailed processes, aiming to advance mechanistic understanding of the interactions among water, ecosystem, and biochemical processes through process-based models, as well as experimental and field data collections. Machine learning has been used to discover patterns in biochemical data sets, as well as uncertainty quantification, and also gap filling or imputation to interpret sparse data sets in time and space. Emerging application of machine learning AI are physics-informed machine learning. And also there is a development of benchmarking training data sets of the watershed science for developing more sophisticated machine learning and AI as well. Next slide, please. So the coastal, ocean, and earth science communities have been using various machine learning applications, particularly surrogate models and emulators have been extensively used. As you see sort of in this table, you can see surrogate models for coastal flooding, ocean models, as well as sea level, sea ice models as well. The emerging AI applications are, for example, emulators for more complex processes such as sediment transport, nutrient fluxes, and also coupled processes, and also learning physics of ice shell fractures, more complex processes from satellite and other observations as well. Next slide, please. And I will pass this presentation back to Scott.
Thank you very much, Haruko. I failed to mention something in our opening slides here. Wanted to give a big thank you to Olga Tweedy, who is a AAAS fellow at DOE, working with Gary and the team, who actually compiled and put these slides together and put them in a nice coherent fashion for us to work through. So I've talked briefly about topics in Earth System Predictability. I hope everyone got the flavor at the beginning. This is really intended to bridge the gap between the kind of machine learning and AI research that happens in OSCAR and the application of AI techniques that happens in BER and EESSD. And so in that vein, we're going to talk about our cross-cutting themes that are very much technique based. So if it's something applied to ESP, it goes in those ESP themed area. This is now about the tools in our toolkit that we need to develop in order to address these grand challenges and to affect a paradigm shift in Earth system predictability. And the first topic, which is one of our cross-cutters, is data acquisition to distribution. So folks may know that Gary's directorate hosts one of the premier observational platforms in the world, the Atmospheric Radiation Measurement User Facility. And this topic is very well aligned with that. How do we use artificial intelligence to improve the way that we even collect our data? So subjects aligned with edge computing and the computing continuum, the Internet of Things, sensors, the Waggle platform that's being developed across several labs here to really, leverage, and folks might know there's this great explosion of small computing platforms. Many people might have, and I thought I had one here, but I don't anymore, a Raspberry Pi, which is a lot of fun for messing around with. They can actually be used to do inference and computing at the edge. But furthermore, things like Jetson, Xavier, AMD, Google's tensor processing unit is coming out. So many of these smaller compute devices which can be placed at the edge for a variety of reasons. One of them is for control at the edge, for complex instruments that may make decisions that are put in a catch-all mode, which tend to be a catch-none mode, to data reduction at the edge, for if we have a thin communication line that doesn't allow the full data to be transmitted to something like the ARM archive, we might want to do environmentally dependent processing of that data to really do data reduction that is more appropriate for the data that is there. However, in all of this, we must think about how do we create things like fair, ready data sets, findable, accessible, interpretable, and I can't remember the R in the end, but cloud computation and storage, monitoring of data flow, again, pushing things like anomaly detection to the edge. Can we detect anomalies at the edge so that we don't lose valuable data in that time it takes for data to go from the instrument to the archive, where we might do machine learning at the archive? Things like drones is really your ultimate edge computing platform, where you might want to actually dynamically modify your sampling strategy with those drones to the phenomena present and the science question being asked. And also looking at things like 5G and beyond, these things, what they call, advanced wireless networks, 6G, where we have very, very low latency, high bandwidth, where you might even be able to actually run simulations at a supercomputer based on the data that's being collected in the field, because the latency is so low and the bandwidth is so high. Another really interesting area, and this gets to a lot of the questions that were being asked in the chat and other places, which is knowledge-informed machine learning. So this, by the way, is different to explainable AI. I'll get to that in a second. This is how do we actually get the knowledge of the scientist and the expert into the algorithms that we're looking at. And the team involved with putting this broke this down into 3 specific areas. They said, kind of think about it like a Venn diagram, where the middle is really where we're really hitting that AI for ESP sweet spot. And that is scientific knowledge, algebraic and differential equations, world knowledge, such as spatial invariants, logic rules, basically the algorithms that are involved in our day-to-day life and in our simulations of things like weather and climate. And this fascinates me because I'm an ex-forecaster. I actually used to sit on the forecast bench back in Australia, and that is expert knowledge. We are all very good at looking at our field, mine being meteorology, and seeing patterns and matching patterns. This kind of wetware or unartificial learning. How do we get that knowledge into the algorithms to do things like detect features? Can we build new algorithms for doing this to apply to the various Earth System predictability topics that we discussed before? And that is, goal-driven knowledge acquisition. And, there are various state-of-the-arts out there already. We've heard a lot about digital twins, which is kind of another way of talking about MODEX as well. Having a model in the loop and being able to continually improve on that model through observations, such that we can close the loop and really tighten the time scale required for knowledge acquisition and development, instead of the usual model of collect data, let it rot in the archive for a year, do some studies, publish some papers, and then hope someone else in a different field picks it up there. And there are many important aspects, including knowledge discovery, knowledge representation, explainability, uncertain quantification, and so forth. Unsurprisingly, well aligned with other subjects that will be discussed here at this workshop. Finally, explainable AI. This is something I've been learning a lot more about in the last year since getting involved in this initiative. And this really gets at the question of how do we get beyond the black box? If we can create a lovely machine learning algorithm that could say, use a short-term storage network and predict what happens in a week based on what occurred now, that's all well and good, but when it breaks, we need to know why. We need to know why it made the prediction that it did. Things like discovering nonlinear interactions in deep neural networks, identification of how local effects propagate into the future, things like layer-wise relevance propagation, and discovery of physics from that knowledge-guided AI. So we need new algorithms and new techniques to really interrogate trained networks and other artifacts created by AI in order to do science, because science is so much more concerned about the why rather than the what. And with that, I am going to hand over to Forrest to talk about our next subjects.
Thanks, Scott. Another important session that we've identified is all of those approaches that may not employ neural networks directly. So these more traditional approaches, which have been around for 30 or 40 years, and complex statistical nonlinear dynamics approaches that are employed. And so these kinds of classical machine learning methods have been used in geostatistics, for data mining, statistical learning, pattern recognition, image analysis, all kinds of things over a long period of time in earth sciences. But they do things like they're used for regression, for supervised and unsupervised classification, for model reduction, or data reduction, density estimation, things like that. and they really complement this newer era of deep neural networks. So this is something that we didn't want to lose in our current workshop. The paradigm of Bayesian statistics enables, work critical to Earth system predictability, including multi-sensor data fusion, uncertainty quantification, data assimilation, and scale bridging, and all sorts of scaling across the spatio-temporal system that we're working with. It's also central to quantifying epistemic uncertainty and large DNNs. In turn, DNNs can aid statistical inference by fast approximation of posterior distributions. On the right-hand side is an example of an Arctic vegetation mapping study that was actually done for DOE's NG Arctic project. And this map was produced using a combination of linear dimensional reduction through principal components analysis, unsupervised classification using a parallel k-means clustering methodology, and a convolutional neural network applied to data fused from multiple sensor sources, multiple satellite products. And so this really checks a whole bunch of the boxes here on these traditional methods, and brings in a neural network into the analysis. Next slide, please. For AI architecture code design, again, we're back to Barb Helen's favorite word, which is code design. We really need to think about what are the architectures of the future computing systems that will be best designed for solving our problems with machine learning approaches, or combinations of traditional, PDE approaches and machine learning. So, HPC systems are already heterogeneous in DOE. We have CPU, GPU system architectures, both current ones that are listed here on the slide and imminent ones. Cloud computing also is providing a lot of the computational fabric for our research community. Network capabilities, what do we need there? So the ESNet is an open network that achieves 400 plus gigabits per second, and a big upgrade for ESNet 6 is coming soon. 5G, how can we best employ 5G to enable these future technologies? Other commercial activities are going on, including spatial data flow reconfigurable architectures for acceleration of these machine learning workloads and scientific computing workflows as well. Edge computing, Internet of Things devices, FPGAs, inference engines, etc. So the key challenges are overcoming multidisciplinary cultural and communication barriers. I don't see that we actually included quantum computing in here, but that's also on the horizon, and thinking about how do we bring those systems in to help us solve our unique challenges in Earth and environmental system sciences. And then partitioning computing capabilities across a wide area networked AI4ESP resource is another thing to consider. So Oscar, our partners in DOE, are also conducting a variety of workshops, including one on reimagining code design. That one already happened. That was back in March. And so there's a report pending there. But there are also some additional upcoming very complementary workshops on model reduction and dealing with benchmark data for AI. Next slide. Neural networks. So this is sort of a large catch-all session that we'll be having, thinking about physics guided neural networks, and how can we then also apply the results from neural networks to help inform physics. At the bottom are a couple of review papers of significance that this group is citing. But we have a lot of these unique challenges of dealing with very large data, which may not be as useful as some of the very small data. And so how do we bring those together to answer our problems and challenges? On the right-hand side of the slide, there's a figure that shows sort of, traditional industrial or commercial applications of machine learning approaches, and then how those might translate to earth science. So that includes things like, object classification, right? Well, we want to do pattern classification and feature detection in Earth science, both from satellite data and from models. Super resolution and fusion. So how can we take low resolution imagery and project something something at a higher resolution? Well, that's what we want to do for statistical downscaling of, say, Earth system model results. Video prediction is another thing. So if we see patterns happening, can we predict what may happen in the future? Well, that's pretty easy to do for a couple of humans walking from one side of the image to another. And maybe based on historical understanding of the Earth system, we can also predict what's going to happen and to do a better job of forecasting with some additional analysis approaches. As well as things like language translation. How do we detect certain signals and translate them to other signals? And so there are all kinds of measurements that we make in the Earth system where this kind of application will be useful. Next, we'll pass it back to Haruko.
Yes, so I'll talk the next 2 slides. So surrogate models. As I mentioned before, surrogate models and emulators have been the most popular applications of machine learning and AI within the white papers and also within the earth science community as well. They have been used extensively in the earth science communities in the past. The main applications include reducing the computational requirement for uncertainty quantification, creating synthetic data sets for predictability studies, model data fusion, calibration, downscaling, upscaling, and others. Recently, more sort of practical, actionable applications such as communication with observing systems and also instrumentation, hardware aspects have been demonstrated. And sorry, my phone. There are many methods available, including Gaussian process models, neural network, physically info neural network, hybrid models, and others. Next slide, please. Hybrid modeling is an emerging field right now. It couples PDE and machine learning methods at the solver levels. Also, it can integrate both data-driven and physics-informed models so that it can couple physics models with experimental and both experimental and simulation data sets within the multiple physics framework and also in the different timescales as well. The challenge has been identified. So for example, most of the applications are mathematical and synthetic studies currently, and the effective applications at the correct level of physics and timescales are challenging. There are computational challenges such as the integration of physics software stack with machine learning software stack. The integration of both type of software methodologies have been challenging. And also there are challenges in training data sets such that it is difficult to have data sets across multi-physics models, as well as across different spatial and temporal scales and resolution. And also the trustworthiness of the hybrid models have been an issue as well. Next slide, please. And again, we thank the session chairs who collected all this information, and also Olga Tweedy to put these slides together as well. And I will pass this back to Nikki.
Great, thank you. I'm going to put up a slide real quick. Oh, no, I can't. That's okay. Maybe I can.
I just stopped sharing, Nikki. You should be able to now.
Thank you. I just want to put up a slide real quick. I don't even need to present it, but I pulled this a little bit ago off of our confirmed participant form. And I just wanted to kind of note that the strong participation from the data sciences computing sciences area. So I really appreciate everyone coming together and reaching out, because originally this was not the perspective I was coming from. So this is really, it's just a great group of people that has expanded and expanded, and it's really wonderful. So I just wanted to show that real quick. So we have time for a couple of questions. There were not questions in the channel. So I would like it to open it to the session leads and DOE that are on the webinar. So session chairs, those of you who are actually behind the screen here, do you have any questions related to what we've put up here, or you think we should maybe ask or entertain? And I did not warn them I was doing that. So with only 7 minutes until our break, I didn't want to.
Nikki, while we wait for a question to come up,
Please.
if you don't mind, I'd like to make a comment. And that is, you might notice in the way in which we've put this workshop together, it does, as Nikki actually said at the beginning, it does feel like 17 workshops all contributing to the one workshop report. We have purposefully given the session leads a lot of agency to create their sessions the way they see fit, with the charge questions in mind and the need to collect the information over these next few weeks to create the session report, which really is why we are here. So if it feels a little bit different going from session to session, that's why.
Yes, and we thank the session chairs in advance for all that work that's going into that, because they're basically holding one, each one on their own. Since it doesn't seem we have too many questions, I will put the links up to the presentations in the agenda. It'll take a little lag to get that onto the website, but for those of you who are directly involved in the sessions and can see the workshop agenda in the Google folder, that's where I'm updating it first, and we'll pull directly from there. So it should happen probably by the end of the day, depending on if the website group can put it on there. All right. Okay, Lynn, thank you. There was a question posted earlier. Are there early ideas coming from the new focus on underserved communities, urban watersheds, et cetera, that we should be considering? Are those changes in time or spatial scales that this will require in models? So I think scope-wise, I think we've definitely included urban, we've included watersheds. Gary, do you want to give us any boundaries on that? I feel like the answer is yes. With the EJ and human side, the answer is yes, but maybe that could be bounded a bit.
Yeah, I don't want to give you any boundaries, because there's no doubt that urban and EJ is a new priority that was given to us, I would say 4 or 5 months ago. So it happened after all these workshop white papers came in. But, given the attention to it, and I think you all know as a preview that we are going to be issuing FOAs that include, let's say, topics on urban and EJ. And this is going to be continuing into the next years. So it might be worthwhile to at least talk about what the capabilities ought to be. And I think I'm on delicate ground here, because I know there are a lot of labs who are vying for ideas that they can perhaps use in response to the FOAs, but it's an important topic. And there's a lot of interest even within the US Global Change Research Program that what the other agencies are pushing with urban and EJ can be leveraged by DOE.
Terrific. Sounds
Nikki,
like
there's a great question in the chat from Jeff, which I think is perfect for Amy, who I think is
go ahead, read
online.
It.
Amy, you able to see Jeff's question there?
Or Amy, you can come on and
I
ask.
am online.
Yeah,
But
that's
there are too many places with chat.
The question
So
is,
there's the Slack and
what-
there's the Q&A.
the question is, what are session leads and panelists' thoughts on ethical AI?
Oh, throw that at me with absolutely no preparation. Sure, I think that we need to talk strongly about the ethical AI and the use of ethical and responsible AI. And it's something that our institute is talking about, because if we're not, and I'll talk about the NSF Institute tomorrow, although I'm going to talk about other things too, but the use of ethical and responsible AI needs to be carefully considered, especially for the environmental justice questions that we've been talking about. Because if we do it not carefully, we could unintentionally replicate the injustice. And if we do it carefully, we could do a really good job of helping to serve environmental justice for everybody and helping to improve understanding and weather prediction for everybody.
Oh, for an unprepared answer, that was well
perfect.
prepared.
Thank you very much. That was wonderful.
Well, it is a topic that I care about, so I can't.
You are very in tune with that.
And there's one there from a couple from Dubai there in the quick Q&A.
Let's see.
I'll ask it if you want, Nikki.
Yeah,
How will cross-cutting atmosphere, ocean, cryo, biosphere AI be handled? It's a kind of a workshop structure question.
So I would say with all the sessions, realize that there is overlap. There is no clear cut bins, boxes, pipes. So that's good on one hand. So I would say you need to look at the atmospheric modeling, particularly, and I've lost the question here. So we had atmosphere, ocean, cryosphere. I would say look at the atmosphere modeling, the land modeling, but then you could, depends on your interest in what you're thinking, you could go some, eco hydrology, hydrology on that. The ocean, was it the oceans? Oh, I'm losing it. Coastal oceans ice session. But then, so I would say those are all going to touch some part of those things that you said there. Plus I'm sure others. And then, so when we get into the idea is that we have these domain-ish understandings of the science and where we are from where we talked about the state of the science and currently, and then drive that conversation forward and move to these cross-cutting sessions that bring everybody together and result into this more collaborative effort from the AI side and the ESP, not separate them. So it is really intermixed. There won't be one session you could go to get that. But that is by design.
We are just about at time, Nikki, I think.
Yeah, I think we probably better stop here because we have a very, very tight time for our panel. So let's please take our short 15-minute break here. Grab what you need to be, and we will come back and we will start right on time because we are really tight with our timing here. And I want to make sure we have plenty of time for our session this afternoon. Thank you, everyone. Hey, Rick, can you hear me?
Yep, I'm here.
Okay, great. I think everybody's on. I saw Prabhat was there.
Yeah, he just checked in.
Oh,
And
hello.
hi, Prabhat.
Hi, Eric.
Hi, thank you for joining us.
My pleasure. Hi, Nick.
And I don't, let's see, is
I
Kirk
see
and
that Kirk,
Grace on as well?
yeah, they were on earlier, at least name-wise.
Of your background, Rick. That was quick.
Yeah, it's called a screen grab, although it's got
Nice.
the
Yep.
got the logo in the middle of it.
Hi, this is Grace. I'm here.
Hi, Grace.
Hey, Grace.
Hello.
And I see Kirk's, well, there he is.
Yeah, I've been here. My green screen just fell over and, there was a cascading effect that knocked over one thing, which knocked over another thing. And so I said, I'm going to just unplug for just a couple minutes here before you see my
There's time.
climatic change in my office.
That'll teach you to try to be professional and have a green
that'll-
screen.
I know. Thank you. Exactly.
I was going to tease Scott for not having a background, but now I understand why.
No, I don't have a background because every time you go on TV, they tell you to take it off. So I spent a long time curating my own background.
They don't like our fuzzy edges.
They do not like the fuzzy edges. Thank you all for coming in. This should be a lot of fun.
Being
Yes.
myself in here.
And just for the fun excitement, we had a few less people and we got some announcements out kind of late, and it's still really amazing what all's already been talked about and what will be. And
Mhm.
I'm just really
think
grateful you
it's-
guys
yeah,
engaged so quickly.
I think it's going quite well so far.
Well,
So in a minute here, I will introduce you, Rick, and you guys can
Okay, yeah, we'll take over. I'll
completely
introduce
take-
myself, then I'll cycle through panelists to say a few views about yourself and why you're here, why you think you're here.
Why you think you're here. Well, we are very grateful you are. Computer's spinning up. All right. Well, everyone, welcome back. Like I said, we're going to start on time here because we got a lot to cover. We're going to have a panel here with a discussion for a bit. So I'd like to introduce Rick Stevens, who's our Associate Lab Director for the Computing Environment and Life Sciences Directorate at Argonne.
Thanks, Nikki, and congratulations so far on a great workshop start anyway.
Thank you.
So what we're going to do for the next 45 minutes or so is a panel discussion really about the big opportunities, trying to expand people's thinking about what might be possible in AI applied to the Earth System's predictability problem. As Nikki said, I'm the Associate Lab Director at Argonne for Computing Environment and Life Sciences, which is kind of a unique combination. I'm also a professor of computer science at the University of Chicago, and I've worked for almost 40 years on computational science, HPC, AI problems. And I was one of the instigators for the AI for Science town halls that Barb talked about in the big push with my collaborators, Jeff Nichols at Oak Ridge and Jonathan Carter and others, Valerie Taylor and David Brown and Barney, pushing the idea of a broad program in AI for science. So with that introduction for me, I'd like to cycle through our three panelists. I'll start with Grace, and each take a few minutes to describe why we've invited you and your perspective, where you're coming from, and then we'll jump into some questions. So start with Grace.
Wonderful. Thank you so much for inviting me. And it's a pleasure to be here. It's been a wonderful workshop so far. And yeah, just off to a wonderful running start with so many great speakers and ideas and thoughts. I am joining this panel with a background in specifically oceanography and Earth system modeling. My PhD is in modeling ocean processes in the GFDL climate model. And with that, I continued on to a postdoc at NASA at the Ocean Ecology Lab. And there I worked again on bringing together satellite imagery to inform climate models and climate prediction. I believe I was invited here today because I submitted a couple of white papers to the AI4ESP white paper call. And yeah, right now I am a consultant at Booz Allen Hamilton, and I did depart from the academic track to join government consulting. And in my current role, I think a lot about hardware and software systems and teams to support AI applications. And I was particularly interested in AI4ESP when the white paper call came out, because it's just this perfect blend of sort of new technologies that are out in the commercial world with the subject matter and functional expertise of Earth system science that I came in with. So with that, I will pass it back.
Okay.
And that's my introduction.
Okay, thanks, Grace. Let me jump over to Prabhat. Introduce yourself, and especially your new gig at Microsoft, I guess.
That's
Tell
right.
us about that.
Right. Happy to reconnect back with the folks in the DOE. So I guess I spent about 14 years in the DOE, first as a researcher with Wes Bethel in Berkeley Lab, and then taking on more of a production role at NERSC, where I believe I was instrumental in helping us think about both big data and AI. Perhaps what's most relevant about my background for this workshop is that I worked with Bill Collins on applying deep learning methods for extreme weather events. So yesterday, much of North California was soaked by an atmospheric river event. So we worked a lot on some of the initial analysis on what kinds of deep learning architectures can be applied for characterizing such extreme weathers. So I guess I did leave the lab after about 14 very productive years, and now I'm at Azure in the HPC team in particular, and we are deploying several large-scale supercomputing systems which are specifically targeted for solving AI training problems. So I'm just glad to be here. Thank you.
Okay, great. Thanks, Prabhat. And Kirk, you're next.
Yeah, thank you. Thanks very much, Rick. Everyone, before I introduce myself, I just want to say that the first 2 hours of this today is just, for me, just beautiful. I felt like it was like the most brilliant syllabus ever for the most awesome graduate level science course that needs to be taught everywhere. I mean, all the things that were covered there is just brilliant. So anyway, so I'm Kirk Bourne. I am background is astrophysics. Have a PhD from astronomy. In astronomy from Caltech 40 years ago. I spent many of those years subsequently continuing my astrophysics research, modeling colliding galaxies. So I was always doing computational science, trying to build models of complex systems. And so there's some colliding galaxy images behind me. So I was doing a data by day and data by night. And what I mean data by day is I spent 20 years after PhD working at NASA on the space science data systems for various space science missions. First 10 years with Hubble telescope, and then another 10 years at the Goddard Space Flight Center working there with the space scientists, but also interacted quite heavily with the Earth science community at NASA Goddard, because there's just so much overlap in terms of the data science and data management and data engineering capabilities between those different departments. And then after doing 20 years at NASA, I did 12 years at George Mason University, where I did as a professor of astrophysics, but basically I was doing data science. We actually we created the world's first data science degree program 15 years ago and taught data science. So I spent 12 years doing that. And then I left academia, much like Grace, 6 years ago, joined Booz Allen Hamilton as the first principal data scientist, an executive advisor, and also the first data science fellow at Booz Allen. And then I retired from what I thought I was retired six months ago. But 6 months ago, after retiring, I became more busy. Now the chief science officer for a new AI startup called Data Prime. And I'm also running my own private consulting, one person business right now. I'd just like to say through all of that, my interactions with Earth System scientists has been very frequent and very often. My touch points with DOE have been frequent and often. Also, I remember working on a paper at a mathematics for petascale computing. I think it was something of that sort several years ago for DOE. I've worked with the air quality people at DOE. I've worked on the smart grid and smart electricity projects with colleagues at DOE. So I feel like I think my last strong connection was at one of those Salishan conferences out in Oregon, which is a very long drive from the Portland airport, but in a beautiful location. So I feel some affinity to a lot of the people who are here today. So thanks for the invitation.
Okay, thanks a lot, Kirk and Grace and Prabhat. So this panel, the purpose of this panel is to really help expand the thinking about what might be possible with AI, and to maybe connect some of the thinking in the AI4ESP to the broader activities in the broader AI community. And so with that goal, we're going to go through a series of questions, and I'll just kind of throw the question out, and then whoever wants to jump in, and then we'll mix it up a little bit and we'll move on to the next question. So so with that model for proceeding, I think we want to start with trying to get our head around what we view, or what you all might view, as the biggest opportunities to use AI in climate and earth science and earth systems prediction, and what might be some of the barriers that have to be overcome to realize the full potential of AI. So why don't we start with Grace?
Sure. Yeah, I think one thing that I've been hearing on the call today, and one thing that I'm excited about as an opportunity area, is the linkage to human systems. And so if we think about the processes and the Earth system predictability from sort of a natural processes standpoint, I've just been so energized and excited about the opportunity to link that to infrastructure resiliency and environmental justice, and maybe even incorporating data that we have about human systems and societies into our predictability framework, and get the appropriate solutions and data and insights to the stakeholders that are really asking for it. And so I think that's a huge opportunity area. One of, maybe it could be a barrier, but I also see this as an opportunity, is a synthesis and the bringing together of everything, all of the solutions that already exist. And we already have so much innovation in so many different spaces. So we've got the Earth system scientists, we've got theory from an individual process level of like physics and biogeochemistry. And then there's the industry innovation that is happening around AI, machine learning, and then computing tools, software infrastructure for collaboration. And I'd love to see all of those pieces come together in a cohesive way, that everyone, in a way that makes collaboration and participation accessible and accessible and kind of open to everyone in the community that's really interested to participate in this awesome endeavor. Okay,
great. Prabhat, you got some thoughts on the opportunities, barriers, maybe, and also maybe on how the challenges of Earth systems prediction could influence the future direction of AI as well?
Yeah, the third one is a little tricky. Let me speak to the, a couple of thoughts on opportunities and a couple of barriers. So first, I think in the DOE, and this is something I realized during my time at NERSC and also as a PhD student, I think there are a couple of unique opportunities that the DOE has in terms of big systems. I mean, all of these exascale machines that are being deployed, Frontier, Aurora, and others to come, it's proven now that deep learning training at scale is an HPC problem. And we in the DOE, I think, have, you in the DOE, I guess, have the best shot at training some of these deep learning models, which I believe that Earth system problems will almost certainly require. High spatial resolution, high temporal fidelity, multivariate data sets. You really need big machines for training. So that's, I think, one of the unique opportunities that the DOE has. You're sitting on petabytes of data in CMIP5, CMIP6, produced by teams of researchers having run simulations across your fleet of compute resources all over the world. So to the extent that deep learning is also constrained in terms of depending on the quality of data, we have superb model simulation output, and really it's high time that we put it all together in training a unified model. Now there are, I think, a couple of barriers which are maybe unique to deep learning. One is really the lack of expertise. The field is moving so fast that it's really only a few key labs such as DeepMind, Google Brain, Facebook AI Research, Microsoft Research. If you are a member of those teams, then you can actually keep pace with the papers that are coming out. But being on the outside, I think it's a little difficult to just keep pace with new methods, how the hardware landscape is evolving, how software is changing. So really, I think either replicating that expertise in the DOE community, in the earth science community, and coming up to speed on methods, keeping pace, and then adapting these methods to your problems of interest, I think that's going to be a big challenge. And I think whether we need new forums for problems at the intersection of AI and earth sciences, new conferences, new journals, that remains to be seen. But I think without such experts, I fear that much of the potential that AI has realized in the industry may not transfer to the sciences. So I'll probably just stop there. We can come back to your other questions on earth sciences being affecting AI maybe a little later, Rick. I think that's
okay. No, that sounds fine. So Kirk, you've had a lot of experience in AI and machine learning as it hits astrophysics, and of course more recently broader areas. So what's your take on the AI opportunities in earth science and vice versa?
Well, I tried to make a short list, and I said I'll come up with my top 10 and reduce it to 1 or 2, and then my list ended up being 15 things. So I guess we're going to have plenty of time in the next half hour to touch some of those. But sort of at the high level, I think one of the questions that popped up during the earlier discussion this afternoon was about is the climate system predictable, or just in general, is a complex system predictable? Certainly a system that's truly undergoing chaos, that's almost by definition, a chaotic system is not predictable, but a complex system can be. But I think of prediction in 2 ways, and this is sort of what I remember having this conversation with someone at the DOE HQ in Washington a few years ago about the difference between predictive analytics and prescriptive analytics. So prediction, basically, in a sense, if you find a correlation between 2 things, as we know, correlation doesn't imply causation. If you find a correlation between X and Y, you can tell me what Y is. If I tell I can tell you what Y is if you tell me the input, right? So given X, find Y. So prescriptive analytics, some people think it's sort of the same sort of thing, but I say it's the exact opposite. It's predictive is given X, find Y. I would say prescriptive is given Y, find X. That is, what's the outcome that you really want to achieve, and then find the causal variables that'll get you there. Find the things that you can tweak, that you can change. I guess you would say in clinical science that would be called the treatment variable. What's the treatment that will lead to the best outcome? And so in medicine, we call that a prescription. In data science, we call that prescriptive analytics. But there's a phrase for prescriptive analytics that I like, and it's called predictive reactive. So in a sense, it's predictive, but it's called predictive reactive because it's basically saying if we see things turn this way or that way in a way that we don't like, how are we going to react? We can predict in advance what is the thing we need to do to react to that outcome as it is evolving. And so that all sounds very good, right? And I guess in some sense, sort of theoretical AI machine learning kind of statement. But I think where it really hit the rubber meets the road is something we also heard about today, which is digital twins, which are these basically sort of model in the loop, as I heard someone describe it, where you basically have a digital representation of the thing you're modeling. And from that, you can learn some of these causal relationships. If you tweak this, what happens? If you tweak that, what happens? If you see something that did happen, you can basically rewind the model. Okay, you can rewind the simulation back to the point where something happened and say, what was the thing that caused that to happen? So if you see something happen in the real world, which is being emulated by this digital twin, it gives you the ability to start seeing what those causal factors are. So I think the challenge is, how do you make all this work in a very complex, enormous system, which has all the human interactions that we've heard a lot about? It's it's a very human system that's affecting climate, obviously. And so how do you interact and integrate all that stuff into a digital twin? And one of the ways I like to think about that is maybe the digital twin should basically, as much as you can find sort of a closed system, I'm not saying I understand necessarily what I'm even saying here, but a region of Earth which has basically almost like a closed climatic system, so it might be the South Pacific Islands or something like that, which is in itself is responding to what the rest of the Earth is doing, and then you can build a very detailed digital twin of that thing and sort of run it through some of these simulations to see what are the things that are causing things to happen there, what can we do to change the things that are happening there, and then apply that insight that we learn on the smaller scale. So using that petascale computing, not just necessarily to make higher resolution of the whole Earth, but hyper resolution of some select region of the Earth. And so then I start getting those insights into sort of another thing I heard a lot this afternoon is about goal-driven data acquisition, which was actually on my list under a different name. So basically knowing what data we need to acquire that we're not acquiring now in order to inform these models and the decisions and that we're using from the models we're building. So what data we need to inform that digital twin, or to inform our predictive accuracy of the climate models. So I could go on and on. I just want to make one final comment on talent, because I have a big proponent of the talent side of this discussion. And I think it's really important for us to realize that we need more than just PhDs attacking this problem. So one thing that's absolutely true of the data science, AI, machine learning community worldwide is it's a huge community of other learners, people who don't pursue a PhD or not interested in pursuing a PhD, and many of whom don't even have an interest in getting a college degree, but they have tremendous capabilities, they have tremendous insights. They also have a wide variety of perspectives that we need. And so when we think about training and bringing in these other perspectives, it's more than just the PhD level training we need to focus on, but also how do we bring in other learners into the DOE community to help them bring their insights and capabilities, sometimes computational capabilities or whatever, to solving the problems we're talking about today.
Okay, thanks. That was really helpful. So, we've summarized some of the big opportunities: data integration, bringing in human factors, creating maybe predictive models that we can mine backwards, or do this prescriptive kind of analysis or causal analysis, perhaps. What do we think are the the key things that the community will need to do differently moving forward to fully embrace AI's potential? So we see AI being used in, there was a whole bunch of discussions in the morning session about existing efforts to apply machine learning in the climate system, and these seem to be been going on for quite a while, whether it's creating subgrid scale physics parameterizations or analyzing the output of models and so on. But I think that there's a sense that there's a broader opportunity, right? That rather than just continuing the path of this kind of incremental use of AI, that there's maybe some more transformative effect that AI could have on Earth system's predictability. And there were some questions, that were asked around what's the most important thing that we want to get out of this? Is it more predictive understanding of extreme events or whatever? So in order to realize some transformative effect on Earth system's prediction, what do we have to do differently than what we're currently doing? And I'm trying to mix it up here a bit. I was reading through some of the questions that we had before, and a lot of them, what we can talk about architecture in a few minutes about how AI is maybe driving computer architectures and so on. But I'm really trying to focus in a bit on, there's this many days of workshops ahead. And if you were trying to give some high-level guidance to the community about how to think about the transformative potential of AI, what would your guidance be to the community? Let me start with Grace.
Yeah, I think one thing I think about that I've been seeing a lot about in the industry side is in AI and machine learning that's been really different, I guess, from sort of how I've seen Earth System kind of past is this rapid innovation and the fast moving innovation. It doesn't have like a grant timeline in the way that sort of like academic labs and PIs typically follow. And so one thing I think about a lot in terms of algorithms for AI models and algorithms for AI for Earth system prediction is that there are so many models and algorithms that get published, and then there are there's like the manuscript, and then there's the data set, and then there's the equations, and then there's no like follow-on AI model maintenance. So for example, every time we get a new set of observations, we can reparameterize, especially if we are having discussions around focused and strategic data collection campaigns. Perhaps we want to update some previous models from past research to retrain and keep up to speed with the latest observations. And I think that's really important, for example, for a changing climate, for a changing Earth system, where the latest observations might exhibit different dynamics from historical trends. And so, yeah, I think about the framework kind of under which Earth system research has been sort of traditionally accomplished. I think about sort of the industry trends of and how industry's been able to go fast. And then I kind of wonder, like, is there a different way to structure this research and this kind of collaboration of PhD scientists and non-PhD scientists and other learners, so that we can all kind of accelerate this field together?
Okay, great. That's really a great perspective. I hope it influences what's being discussed in the next couple of weeks. Prabhat, what's your take on the how we transform what the climate science community usually does?
Yes, Rick, let me maybe put something controversial out there. I think DOE Oscar has been very successful, partly in that it has a great track record in deploying big systems, scaling codes. But also I feel like the applied math program is really the rock. Now, I feel that in some ways, there is a very big cultural difference between first principle theory, as encapsulated by our successful applied math colleagues, and the empiricism of modern data science and deep learning. And I feel that because the DOE has been so successful based on first principle theory, there is a little bit of resistance and skepticism of the rise of deep learning methods, and I think that's been holding the DOE back. So I think I want to, in order of just to put out a suggestion of things to do differently, I think becoming a little more comfortable with the empirical success of deep learning, waiting for the formal theory to catch up, waiting for the formal proofs to catch up, waiting for interpretability and explainability methods to come down the line. They are coming, but they're not here yet. And I think just being open, there are generations of scientists who may have explored neural networks in the 80s and 90s, and they may be, again, skepticism that, like what's different this time around. But fundamentally, I think there are enough proof points in the industry that this wave of neural networks is working. And I think, I believe that DOE's closed roots in first principles theory has really held that back. So anyways, I would say that doing what it takes to customize, adapt, tweak, deploy deep learning in your applications that you care about, keeping tabs on how the theory is moving along, contributing to that theory if possible, but not just demanding that there be a formal proof of deep learning working and blocking progress on that, I think is not going to be productive. So anyway, I just wanted to maybe just get that out there.
Okay, great. That's a great viewpoint. Actually, shared by a lot of people, really. That and some of the leaders, like in AI, that are very empirical, empiricists in some sense, and whether the theory catches up or not, they're moving ahead. So, Kirk, what's your take on the transformative potential?
Well, first, I agree strongly with what Grace and Prabhat have just said. I mean, I did Grace's comments about sort of changing the culture almost of research grants, because when I first sort of tiptoed into the machine learning world about 20-something years ago, after nearly 20 years doing astronomy data systems and astrophysics research, discovered this amazing mathematical world of machine learning. I would go to machine learning research conferences, and this was like 20 years ago. And the machine learning research conferences were basically of the type that Grace described, and that is, people would write a paper, produce an algorithm, use some data set, publish, and then move on to the next thing. And it was sort of like not the follow through. There was not the maintenance of the model. There was not like a deployment of the model and further sort of value created from it, other than an academic value. So I think we need to have a mindset that it's not just a science experiment we're doing. It really is just a change of the way we're thinking and doing things. And I think what Prabhat really hit upon in my mind, all his comments were great, but a way I like to describe it is that if people really understand, people and a lot of scientists don't understand this, and it took me a while to understand it. There's a real difference between machine learning and deep learning. Machine learning is a lot like sort of traditional sort of model building that scientists do. You have a set of features that you think are the features that are going to again, if you think of a model as an input leading to an output, and the output might be a prediction. Again, it's this sort of y equals f of x sort of thing, right? And so you know what the input is, and in machine learning, what you do is you train the model on the input and the output on the x and the y to find out what the best y is. What function, excuse me, the correct function that maps those two things. That's machine learning. So it's a lot like when I used to do my galaxy collision models, right? I mean, I knew what the physics was. I knew what the inputs were. And I was trying to produce an output, which was matching my model to this wonderful thing I see in the sky in my images. But deep learning basically learns what the features ought to be. So there's this layer in deep learning, which is called the autoencoder, where it takes all those inputs and outputs and says, what is the succinct, distinct set of features that are most predictive of from the input to the output. I mean, in a sense, it leaves the feature engineering step to the network, not to the scientist. And so what happens is you get into this problem with the explainability of the model, because it turns out the best feature to predict, let's say, this particular climate variable, is some nonlinear combination of these 50 other variables that you've collected, types of measurements you've made with your satellites and ground truth and sensors and so forth. And so how do you explain that to someone? It's like this crazy nonlinear combination of all these other things. So there's an explainability challenge. That is going to be a real challenge. But the cultural challenge is to realize that we should if we actually go with AI and deep learning, we need to understand that the deep learning is going to help us find what are the most explanatory variables, the most predictive and prescriptive variables that lead to the outputs that we're both predicting, and earlier, like I was saying about prescriptive analytics, the things that will lead to particular outcomes given how you tweak the input. And so that's a very different way of thinking about modeling, which was very different from the way I learned about modeling as a young scientist and used it all my career. And so there's sort of a mind shift in that regard, but also, as Prabhat was saying, the explainability, the theory of, and the accuracy of explainable AI is going to catch up with us. We shouldn't wait for it to catch up with us. I mean, in terms of like, we can still build models that are valuable, that don't, I hate to say it this way, but they don't have quite the same impact as other models that do have impact, right? So if I build a deep learning model of colliding galaxies, it doesn't impact anybody personally. But I mean, there's places where we can start learning how to do this, in impactful ways that are not, like human impactful, if I can say it that way. I'm sort of dancing around how to say it, but I mean, places where we can still make great progress in the research here by understanding these capabilities.
Okay, great. So I want to shift topics a little bit. One of the really successful areas in where AI is being applied in industry is pushing AI methods out to the edge. And in the climate research community, we have a lot of opportunity for sensing and inference at the edge versus the big central models. So what's your take on how we should leverage the opportunity of AI at the edge and the great kind of expansion and maturity and availability of like IoT technologies and small compute devices like some of the stuff that Scott mentioned, into building kind of a more integrated ecosystem where AI might be in many different places, contributing to advancing climate understanding. So Grace, thoughts on that?
Yeah, I think it's, I think about the data reduction and the edge AI computing problem in terms of sort of like a observational and observational data curation perspective. And so, as insofar as we have, X amount of existing observational data now, and then we want to expand on that, that bank of observational data that can be used and leveraged to train and develop new models, then how can we, I guess strategically think about what are the observations that we need, and then how can we collect more data from our observing system kind of efficiently. So if we have hardware requirements and hardware limitations for observing, for example, from an imaging perspective, if we don't need like all the imaging bands and we know that this one band is what we're looking for, or if we're kind of smartly detecting a certain shape or feature in our imagery, maybe that's all we need to collect, and then we can collect more of that relevant data. So yeah, I think it kind of lends itself into that conversation about the observing strategy, observing smartly, and then kind of think about what is the data set that we want to come out of it to train the models that we need. So yeah, that's kind of maybe some initial thoughts.
Prabhat, you have thoughts on this? It must be a big strategy at Microsoft Azure, right? Connecting the cloud to the edge. And how should we approach this problem?
I guess I'll mention an anecdote from grad school. So I guess when I, for my qualifiers in my second year, I'd actually started working with David Romps on augmenting the ARM array of instruments with a couple of stereo cameras in the field. And, Berkeley's weather is boring most of the time. So we had some deployments in Florida looking at deep convective clouds and using the stereo camera system to come up with an estimate for the top of the cloud, and then estimating the vertical velocity of the cloud and so on and so forth. So really it felt like, application of basic computer vision stereo reconstruction technology to the existing ARM suite. And really, I mean, holistically speaking, the DOE has just such a wonderful array of in-field deployments like you have some satellite-based sensors, some ground-based sensors, ocean sensors, so on and so forth. So it does feel like the state of the art in deploying, applying modern deep learning, or for that matter, really conventional machine learning techniques to do multimodal analysis is lacking. I think there's just so much opportunity there. And really, I think you could think about in situ data reduction, data compression, in situ detection of features, in situ filtering. There's just so much potential there. So I feel that the most extreme example in the industry really is around self-driving cars. There are these amazingly well instrumented cars that go around and collect data about the world. And then all of that data, I mean, there are decisions, of course, that the car makes, but all of that data is sent back to a supercomputing system to refine the control logic for the car, and then that gets pushed out and so on and so forth. So there is a federated nature to how the sensing happens and how perhaps the control is executed, but a centralized way where you are creating a model for the world's most accurate decision-making car. So I think compare that sophistication to the way we think about data processing right now in the DOE. There's a lot to do there, I guess.
Okay, great. So Kurt, I mean, in your experience, and especially now in your consulting, I mean, do you have advice on how to construct an overall computational ecosystem with edge connected to the core and everything?
I do actually. I've been creating notes to write a book on this very topic. So yeah, how many hours do we have here? No, I just want to put up a prop. So when I was teaching a graduate course on sensor networks, and which is the phrase we used before Internet of Things, and talked a lot about data, and my students, I had a question on the final exam to describe some applications of sensor networks, and one of the students wrote that we can process in situ data. So I wonder if that was a nitrogen carbon compound or something. I didn't know what it was. So I said, what is that? And he said, well, you talked about it in class all the time. I said, I did? He said, yeah, you talk about all that in situ data. Thank you, Prabhat, for that in situ data reference. So no, seriously, I think, oh yeah, that was serious also. I love the comments I'm hearing. I mean, I'm just following these two people. I feel like I got to come up with something new and interesting. I mean, the things that Grace was saying about how did she describe it? The observational data curation, or efficient resource limited observational curation. To me, that's the real, what I find is the ultimate value proposition of edge computing. Is in the same way a self-driving car, I always revert back to an autonomous vehicle as my example. In a self-driving car, you have these sensors, right? You have cameras, you have LiDAR, you have radar, and you don't necessarily need to save all that stream of data. You need it to make the decision of what to do next. And the one thing you do not want to do is collect all that imaging data and send it back to some cloud somewhere and compute for 10 or 15 minutes to decide what the car should do. The car has to react and decide what to do in that moment. But you don't need to keep all that data. So edge computing is a form of, to me, of both, what I call putting the intelligence where your data is. Okay, so moving the algorithms, the intelligent AI, machine learning, to the data. But it's also a form of data triage, which taps into what Grace was talking about, I think, which is knowing what data is the most important data to deal with, to respond to take action from, and maybe even what data we ought to save and send back to the data center, that sort of thing. And so edge computing has a lot of value propositions in terms of smart deployments of anything, even satellites in space. I mean, changing its sort of targeting schedule to if it sees something developing in the clouds over the Atlantic Ocean, or over a particular environment like a flooding situation or a hurricane or a tropical storm or a wildfire even, then it can redeploy its or basically interrupt its own predetermined scheduling to do an autonomous decision. I'm going to focus on this emerging event right now. Okay, so these sort of things that you imagine happens in deep space probes, where there can be no human controller telling the satellite at the probe as it's passing Pluto, hey, turn left and look at this thing, because the light travel time is many hours in that case. And so data triage, both in terms of what data to use, how to use it, when to use it, which to say, what not to say, but also in terms of smart scheduling, smart decision making at the edge, and especially and sort of redeploying and rescheduling your sensors to focus on the thing that's really most important at that moment.
Okay, great. So I want to kind of close us out by just getting some quick response to one of the questions posed by the audience, essentially, is, and I'll just boil down the question, what's the opportunity for DOE and the DOE community to collaborate with industry on this problem? Because industry is building out a huge amount of infrastructure and capability. So just briefly, what do you see as the opportunity for collaborating with industry? Grace?
Yeah, one key thing that I think about in terms of maybe what we were discussing earlier with all of the people that are involved or maybe could be involved to really transform this field. I think about the personas and the stakeholders in the AI lifecycle management and all of the phases. And I wonder sometimes about where is a researcher who is deeply trained and familiar with Earth system processes, where is their role best served within that AI lifecycle management? And then think about where does industry have sort of a leading expertise that can come in and support and collaborate with academics in that way.
Okay, great. Pravat, what's your sense? Industry, do we collaborate? Opportunities for you?
There's a lot of opportunity, right? So if you look at Azure or AWS or GCP, the range of hardware that's available to you. I mean, Rick, you've done that at ALCF. Flavors of CPUs, GPUs, FPGAs, ASICs. I mean, there's just an immense opportunity to take specific workloads, run them on such hardware, and see what hardware is actually best suited for your workloads. I think there's just a lot to do there. But I actually think that there are broader opportunities in the software space. So first, the software stack, I would claim, has been independently developed by the industry. And in the DOE, we are mostly just using that stack. But bringing all of the lessons learned from the HPC community as it pertains to performance optimization and scaling, I think there is some technology transfer that could happen there. So I hope that happens in the future. I think that there's an even more potential really for collaborating on methods. So, I might have dinged the applied math community a bit, but just coming back to that, there's just so much sophistication that we have built up in applied math for 40 years. So just bringing that back, the methodology back to deep learning and contributing ideas on how do we formally prove that these methods work, or when do they apply, when do they not apply, characterizing generalization limits, so on and so forth. I think there's a tremendous opportunity there as well. So I would say that that's probably my take: hardware, software, and methods.
Okay, great. And Kirk, just super briefly.
Yeah, thanks. I'm still riding on the coattails of my pre-speakers there, but I just want to add one more, and that is, I think there's so much development around smart cities, smart homes, smart cars, smart transportation, smart energy, and industry, and all those things impact climate and sustainable development. All those things that we're looking to impact with what AI at DOE is doing. I think tapping into what industry is already investing in for those particular types of projects, lessons learned, methodologies, infrastructure, just like Prabat was talking about. I think that's where we're going to really find value, because they're already addressing a lot of these issues and building out things and getting lessons learned from those things. And those things impact climate and Earth system predictability. So start having those conversations.
Okay, great. So I want to thank the panelists. I see Nikki there. I'm going to turn it back off. So thanks, Grace, Kirk, Prabat, for your insights and for participating. And Nikki, I'm going to turn the mic back over to you.
Thank you very much. Thank you all. That was a really wonderful panel, and I really appreciate you sharing your insights with us, not only on what we're thinking about already, but what are the possibilities and how could we better interact and work together. And that was just an absolutely fabulous panel. Thank you, Rick, for hosting that. I really appreciate it. And I hate to cut short and run, but we do have our first session, and luckily Ruby has a very broad range of science and has hosted many key workshops. So she is our first session lead and quite capable of making a quick switch over, which this will require. So thank you all very much for attending the public portion of our workshop today. And we will jump off, and I hope to see you in the next public portion or sooner in the session. Thank you, everyone.